The replacement for WEP from the Wi-Fi Alliance was WPA, or Wi-Fi Protected Access. It was introduced in 2003 as a temporary measure while the Alliance finalized their specification for what would become WPA2, introduced in 2004. WPA was designed as a short-term replacement that would be compatible with older WEP-enabled hardware with a simple firmware update. This helped with user adoption because it didn't require the purchase of new Wi-Fi hardware. To address the shortcomings of WEP security, a new security protocol was introduced called TKIP, or the Temporal Key Integrity Protocol. TKIP implemented 3 new features that made it more secure than WEP. First, a more secure key derivation method was used to more securely incorporate the IV into the per-packet encryption key. Second, a sequence counter was implemented to prevent replay attacks by rejecting out-of-order packets. Third, a 64-bit MIC or message integrity check was introduced to prevent forging, tampering, or corruption of packets. TKIP still used the RC4 cipher as the underlying encryption algorithm, but it addressed the key generation weaknesses of WEP by using a key mixing function to generate unique encryption keys per packet. It also utilizes 256-bit long keys. This key mixing function incorporates the long-lived Wi-Fi passphrase with the IV. This is different compared to the simplistic concatenation of the shared key and IV. Under WPA, the pre-shared key is the Wi-Fi password you share with people when they come over and want to use your wireless network. This is not directly used to encrypt traffic. It's used as a factor to derive the encryption key. The passphrase is fed into the PBK-DF2, or Password-Based Key Derivation Function 2, along with the Wi-Fi network's SSID as a salt. This is then run through the HMAC SHA-1 function 4,096 times to generate a unique encryption key. The SSID salt is incorporated to help defend against rainbow table attacks. The 4,096 rounds of HMAC SHA-1 increase the computational power required for a brute force attack. I should call out that the pre-shared key can be entered using 2 different methods. A 64-character hexadecimal value can be entered, where the 64-character value is used as the key, which is 64 hexadecimal characters times 4 bits, which is 256 bits. The other option is to use PBK-DF2 function, but only if entering ASCII characters as a passphrase. If that's the case, the passphrase can be anywhere from 8 to 63 characters long. WPA2 improved WPA security even more by implementing CCMP, or Counter Mode CBC MAC protocol. WPA2 is the best security for wireless networks currently available, so it's really important to know as an IT support specialist. It's based on the AES cipher, finally getting away from the insecure RC4 cipher. The key derivation process didn't change from WPA, and the pre-shared key requirements are the same. Counter with CBC MAC is a particular mode of operation for block ciphers. It allows for authenticated encryption, meaning data is kept confidential and is authenticated. This is accomplished using an authenticate then encrypt mechanism. The CBC MAC digest is computed first. Then, the resulting authentication code is encrypted along with the message using a block cipher. We're using AES in this case, operating in counter mode. This turns a block cipher into a stream cipher by using a random seed value along with an incrementing counter to create a key stream to encrypt data with. Now, let's walk through the 4-way handshake process that authenticates clients to the network. I should call out that while you might not encounter this in your day-to-day work, it's good to have a grasp on how the authentication process works. It'll help you understand how WPA2 can be broken. This process also generates the temporary encryption key that'll be used to encrypt data for this client. This process is called the 4-way handshake, since it's made up of 4 exchanges of data between the client and AP. It's designed to allow an AP to confirm that the client has the correct pairwise master key, or pre-shared key, in a WPA PSK setup, without disclosing the PMK. The PMK is a long-lived key and might not change for a long time. So an encryption key is derived from the PMK that's used for actual encryption and decryption of traffic between a client and AP. This key is called the pairwise transient key, or PTK. The PTK is generating using the PMK, AP nonce, client nonce, AP MAC address, and client MAC address. They're all concatenated together and run through a function. The AP and client nonces are just random bits of data generated by each party and exchanged. The MAC addresses of each party would be known through the packet headers already, and both parties should already have the correct PMK. With this information, the PTK can be generated. This is different for every client to allow for confidentiality between clients. The PTK is actually made up of 5 individual keys, each with their own purpose. 2 keys are used for encryption and confirmation of EAPOL packets, and the encapsulating protocol carries these messages. 2 keys are used for sending and receiving message integrity codes. And finally, there's a temporal key, which is actually used to encrypt data. The AP will also transmit the GTK, or groupwise transient key. It's encrypted using the EAPOL encryption key contained in the PTK, which is used to encrypt multicast or broadcast traffic. Since this type of traffic must be readable by all clients connected to an AP, this GTK is shared between all clients. It's updated and retransmitted periodically, and when a client disassociates the AP. That's a lot to take in, so let's recap. The 4 messages exchanged, in order, are the AP, which sends a nonce to the client then sends its nonce to the AP sends the GTK, and the client replies with an ACK, confirming successful negotiation. The WPA and WPA2 standard also introduced an 802.1x authentication to Wi-Fi networks. It's usually called WPA2 Enterprise. The non-802.1x configurations are called either WPA2 Personal or WPA2 PSK, since they use a pre-shared key to authenticate clients. We won't rehash 802.1x here, since it operates similarly to 802.1x on wired networks, which we covered earlier. The only thing different is that the AP acts as the authenticator in this case. The backend radius is still the authentication server, and the PMK is generated using components of the EAP method chosen. While not a security feature directly, WPS, or Wi-Fi Protected Setup, is a convenience feature designed to make it easier for clients to join a WPA PSK protected network. You might encounter WPS in a small IT shop that uses commercial SOHO routers. It can be useful in these smaller environments to make it easier to join wireless clients to the wireless network securely, but there are security implications to having it enabled that you should be aware of. The Wi-Fi Alliance introduced WPS in 2006. It provides several different methods that allow a wireless client to securely join a wireless network without having to directly enter the pre-shared key. This facilitates the use of very long and secure passphrases without making it unnecessarily complicated. Can you imagine having to have your less technically inclined friends and family enter a 63-character passphrase to use your Wi-Fi when they come over? That probably wouldn't go so well. WPS simplifies this by allowing for secure exchange of the SSID and pre-shared key. This is done after authenticating or exchanging data using one of the 4 supported methods. WPS supports PIN entry authentication, NFC or USB for out-of-band exchange of the network details, or push-button authentication. You've probably seen the push-button mechanism. It's typically a small button somewhere on the home router with 2 arrows pointing counterclockwise. The push-button mechanism works by requiring a button to be pressed on both the AP side and the client side. This requires physical proximity and a short window of time that the client can authenticate with a button press of its own. The NFC and USB methods just provide a different channel to transmit the details to join the network. The PIN methods are really interesting and also where critical flaw was introduced. The PIN authentication mechanism supports 2 modes. In one mode, the client generates a PIN, which is then entered into the AP. In the other mode, The AP has a PIN, typically hard-coded into the firmware, which is entered into the client. It's this second mode that is vulnerable to an online brute force attack. Feel free to dive deep into this by reading more about it in the supplementary readings. The PIN authentication method uses pins that are 8 digits long, but the last digit is a checksum that's computed from the first 7 digits. This makes the total number of possible pins 10 to the 7th power, or around 10 million possibilities. But the PIN is authenticated by the AP in halves. This means the client will send the first 4 digits to the AP, wait for a positive or negative response, and then send the second half of the PIN if the first half was correct. Did you see anything wrong with this scenario? We're actually reducing the total possible valid pins even more and making it even easier to guess what the correct PIN is. The first half of the PIN, being 4 digits, has about 10,000 possibilities. The second half, only 3 digits because of the checksum value, has a maximum of only 1,000 possibilities. This means the correct PIN can be guessed in a maximum of 11,000 tries. It sounds like a lot, but it really isn't. Without any rate limiting, an attacker could recover the PIN and the pre-shared key in less than 4 hours. In response to this, the Wi-Fi Alliance revised the requirements for the WPS specification, introducing a lockout period of 1 minute after 3 incorrect PIN attempts. This increases the maximum time to guess the PIN from 4 hours to less than 3 days. That's easily in the realm of possibility for a determined and patient attacker. But it gets worse. If your network is compromised using this attack because the PIN is an unchanging element that's part of the AP configuration, the attacker could just reuse the already recovered WPS PIN to get the new password. This would happen even if you detected unauthorized wireless clients on your network and changed your Wi-Fi password. WPA2 is a really robust security protocol. It's built using best-in-class mechanisms to prevent attacks and ensure the confidentiality of the data it's protecting. Even so, it's susceptible to some forms of attack. The 4-way authentication handshake that we covered earlier is actually susceptible to an offline brute force attack. If an attacker can manage to capture the 4-way handshake process, just 4 packets, they can begin guessing the pre-shared key, or PMK. They can take the nonces and MAC addresses from the 4-way handshake packets and computing PTKs. Since the message authentication code secret keys are included as part of the PTK, the correct PMK guess would yield a PTK that successfully validates a mic. This is a brute force or dictionary-based attack, so it's dependent on the quality of the password guesses. It does require a fair amount of computational power to calculate the PMK from the passphrase guesses and SSID values. But the bulk of the computational requirements lie in the PMK computation. This requires 4,096 iterations of a hashing function, which can be massively accelerated through the use of GPU-accelerated computation and cloud computing resources. Because of the bulk of the computations involving computing the PMK, by incorporating the password guesses with the SSIDs, it's possible to pre-compute PMKs in bulk for common SSIDs and password combinations. This reduces the computational requirements to deriving the PTK from the unique session elements. These pre-computed sets are referred to as rainbow tables, and exactly this has been done. Rainbow tables are available for download for the top 1,000 most commonly seen SSIDs and 1 million passwords.